Hey everybody.
How you feeling?
Feel good. Feel better today.
That's good.
Still a little bit tired, but I think yesterday I was feeling a little bit feverish, so today is definitely an improvement.
Nice. Are you sore?
Not really, actually. I was more sore from the first dose for some reason.
That's good. As long as you're feeling better.
Mhm.
Are we using ANSYS today or on Thursday?
Thursday.
Okay.
Yeah. Hi, Darren.
Hey, how's it going?
Good, good. How are you?
Just got off of spring break. Just felt like it was too short.
It's always too short. It's never long
Always.
enough.
Never long enough.
We're able to rest and recharge a little bit at least.
What was that?
Were you able to at least rest up a little bit or catch up on sleep a bit?
Oh yeah, a lot of resting. That was the main thing.
That's good.
Just
That's good.
sleeping 3 or 4 days, just napping all day long. It was nice.
Nice, nice.
Felt a
Sounds
little
good.
burnt out, I feel like,
Mhm.
before that. Past 2 semesters, a little burnt out. Because senior design, it's rough.
Yeah, it's always really rough. That's why whenever I teach this class, it's mostly seniors, and like there's just parts of the semester where like a lot it feels like a lot of the class just is not there. But I understand that it's because of senior design.
Yeah, you were once a student, so you know how it feels.
Oh yeah, oh yeah.
Yeah, awesome.
Professors were once students? I thought they were just born farm fresh.
What? They were students?
Yeah, he
Yeah, I
just
was uh,
popped.
I was just born like this, just giving Zoom lectures right out of the
Yeah,
blue.
he was just popped out of the ground and chose violence and 12-page homeworks. It's just, I thought that's how it always was.
I thought he was born a genius, just already knew all this info and just teaching.
No, no. I learned it in school just like everybody. All right, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing? How's everyone's spring break? Good, good. I see one thumbs up. That's good. Yeah, it's spring break's always never too long enough to it's never long enough to really do everything that you need to do. I'm sure you know a lot of you guys are working over the spring break too. So, but at least you know hopefully everyone's able to catch up on a little bit of sleep and maybe catch up on a little bit of work and you know get some rest because you know ultimately your health is going to be you know that's the most important thing you have to take care of. Okay, and so we're back and so for and so, you know, we have about 6 more weeks ahead of us in this semester, so still have quite a bit to go, and especially for this class. So, and so if you haven't visited the Canvas site since coming back, there's quite a few new things on there, quite a few deliverables. And so the first thing that's posted that's going to be due this Friday is the project proposal. Right? And so we talked about that I think right before the spring break, which is you know the nature of the final project. You're going to be performing an ANSYS analysis, ANSYS simulation on basically anything of your choice. And so I've spoken to you know quite a few people in this class already about your final projects, and so far you know a lot of them seem really good. But you know just even if we've talked about it before, you know still submit the proposal this Friday. It's just a simple kind of 1-page thing. Show me a screenshot and just describe to me what you want to do, and then I'll check it out for completion. And so that's going to be due this Friday. And to help you guys out, just to kind of see, if you want to see some samples of what people have done in the past, I posted some sample material. And so I posted a couple example proposals. And so if you're not sure what to write in your proposal or how to structure it, you can look at those. I've also put samples for progress reports. And so you can look and see what those are like. And I think probably the thing that's going to be most interesting to people is sample final reports. And so the final project, you know, I haven't changed all too much over the last couple of years. I mean, the dates and deadlines have kind of changed. That's probably the only thing. And so, you know, if you read those final project reports from, I think they're both from a couple of years ago, they'll give you a really good idea about generally what I expect from this final project and you know what you need to do in order to do really well. Okay. All right. And so besides that, there's another homework that's posted. And so that's going to be homework 3, I believe, in this class. And so that's going to be due next Friday. And the subject for that homework 3 is going to be all the stuff that we covered kind of before the spring break. So everything on strong forms, weak forms, and finite element forms. And so the timing for this homework is a little bit awkward just because, you know, it's been a while since we covered that stuff. But I didn't want to overload you guys either, you know, right before the spring break or during the spring break. So I kind of waited until now to assign it. And so in order to do that homework, you have to look back a couple of weeks and see, you know, what we did for things like the strong form and the weak form and the finite element form. And so, you know, it might take a bit of time to kind of look back and kind of remind yourself what we were doing at that time. But that's why I kind of gave you guys 2 weeks to do that. So that's going to be due next Friday. And so definitely get started on that early. You know, it's I know Alex was joking before the class that it's you know, I'm getting famous for the 12-page homework. So this is another one of those where it's going to take you it's going to take a bit of time. I will say it's not as tedious as the beam and the trust stuff, and so it's not just you know just mindlessly copying down stuff into a matrix. And so you know it's not the calculations are a little bit more interesting than that, but it is going to take you guys a while. And so you know I would definitely start sooner rather than later. You know if you're struggling on that, definitely you know hit me up. You know, send me messages on Discord, email, or come to office hours, and you know, I'm happy to help you. Okay? But definitely start on that sooner than later. Okay? And the last assignment that I posted on Canvas was the next ANSYS activity. And so that's going to be due not next Friday, but the Friday after that. And so we're going to be doing our next ANSYS activity on Thursday. I think you guys will enjoy that one because it's you know we'll be simulating a car crash. So I think that one's pretty new. And so that will be due 2 weeks. So I'll give you guys basically 2 weeks to do that ANSYS activity as well. So there's a lot kind of on the docket for this class, but you know definitely get started early and you know start working on it sooner. That way you know things don't kind of sneak up on you at the very end. Okay.
Sorry, Professor. When was the homework due again?
The homework is due next Friday, and so okay, that's the 16th, I believe.
Gotcha. Thank you.
Mm-hmm. Yeah. Yeah. So I will warn you too about the ANSYS activity on Thursday that it's probably out of all the ANSYS activities, it's probably going to be the most taxing on your computer. And so if your computer's kind of been struggling to run ANSYS up to this point, I would highly recommend that you use the virtual computing labs to do this activity. Because compared to all the other activities, this one is going to be the most taxing. And if you have kind of a slower computer, it's really going to show in this activity. So, go back to the first week. I posted a video on how to access the virtual computing labs, and running the activity on that one will be a lot faster. Right? So for Thursday, if you don't really have faith in your computer, I would use that compared to your own machine. Okay. Okay. So there was a lot of announcements. So any questions on anything before we get started today? Okay. Right. So the topic for today is we're gonna pick up and continue talking about 2D element types. But actually, before we do that, someone asked me a really good question over the break, kind of just asking about just the general structure for the class and how everything fits together. And I want to spend the first maybe 5-10 minutes talking about that, because I thought it was a really good question. Especially because I know in this class that we've been doing just a lot of stuff, and it might not really connect. It might not really be clear how everything connects. And so, I'll be perfectly honest with you guys that, I think this is the third time that I'm teaching this class. And every time that I've taught this class, I've really done something different with it, because nothing has really quite felt right about finite elements, the way that I've been teaching it. And this semester, I've probably taken the most risk and the most kind of different things that I've done before. And so, I do want to kind of step back and kind of talk a little bit about how everything fits in. Especially how everything fits in with ANSYS. So hopefully that will make things a bit more clear. And as always, it's always a tough situation, because as an instructor, you always kind of want to find what's the best way to kind of present a certain topic, best way to teach it. But really, the only place to really try it out is in real class, because you can kind of theory craft things all the time and think about how things are going to go, but you don't really know how things are going to go until you actually try. And so, I just want to just take a moment to say, thank you guys for your patience. I know as an instructor, when I try things, not everything's going to be a home run. Actually, most things end up being kind of a ground out. And so, that's and unfortunately, kind of you guys are the ones that kind of have to deal with that. So, I appreciate you guys being patient with me and kind of working through the growing pains with this. Because it's a great thing. It's good. When we can try out new things, and I know it's not always comfortable, but I appreciate you guys. That's kind of the main thing. But let's kind of just take a step back and see how everything kind of fits together, right? And so far, the way I kind of see this class and the way I kind of design it is we've kind of covered three kind of big areas so far. Right? So the first big area that we talked about was kind of trusses, kind of all the direct stiffness stuff that we did kind of for the first midterm. So all the first midterm stuff. Right? And so this is trusses and beams, and we'll put springs in there too. Okay. So this was kind of the big first area that we went over. And kind of what I wanted you guys to kind of take away from this is kind of just the general finite element process, right? And so if if we kind of think back to when we were doing this unit, we did things like, we looked at our structure, we broke it up into elements, or the structure was kind of broken up into elements for you, and then you kind of went through the whole finite element solution procedure, right? And so we did things like we started with, we wrote down all the element stiffness matrices. We assembled them. And we applied boundary conditions. And then we solved, right? Okay. That was kind of the whole point of this first unit. So, I would say, that first unit was that was kind of the big new risk that I kind of took with this class. And so, and it ended up being a lot more tedious than I thought it was. But what I wanted you guys to get from this is that this whole process here of, doing element stiffness matrices, assembling them into one big system, applying boundary conditions, and solving it, most of the time using a computer, this is the finite element process. So this is kind of, no matter what kind of finite elements that you do, this is what, this is what you have to do for that. And the reason I kind of chose to do trusses and beams, because those are, hopefully, those are things that you've kind of seen before in previous classes. And so I was hoping to kind of latch onto those things and kind of put it within a finite context. Okay? But a couple points that during this unit that we kind of glossed over was, first of all, how do we even obtain these element stiffness matrices to begin with? And so if you kind of remember from that unit, I gave you, say we have a truss element. Here's the element stiffness matrix for that truss element. And I just kind of gave it to you without really any explanation, right? And so if you have a beam element, here's the element stiffness matrix for that beam element. Really no explanation for that. And so that's kind of one kind of point that we kind of glossed over in that first section. And the second point that we kind of glossed over in that first section was, here's a structure, and the structure is already broken down into elements for you. But in reality, that doesn't always happen, right? And so kind of a 0th step right here is the meshing, right? So mesh geometry. Okay. And so that was kind of another thing that was I kind of just gave that to you guys, without really thinking about it, which is okay. Because the thing with finite elements is that it's such a involved process. There's so many steps to it. It's kind of hard to take it kind of step by step and kind of piece it all together. And so with this class, I kind of did it kind of reverse, where I said, here's the entire process, and here's a way that we can go from structure to finite element solution, and I kind of just help you out along the way, right? And so the next few units, what I wanted to do was I wanted to focus on kind of the steps that we've kind of glossed over for here. And so that's kind of the strong form, the weak form, and the finite element form. That unit kind of focused on how do we obtain these element stiffness matrices. Right. And so this is of course the subject for homework 3. And the main thing that I wanted you guys to take away from this part is, how can we derive element stiffness matrices from a differential equation? Okay, because this is traditionally how it's done in any kind of finite element software. So underneath the hood in ANSYS, ANSYS isn't coming up with element stiffness matrices just like magic, right? And so the way that ANSYS produces this element stiffness matrices is that it starts from the governing equations. And so it starts from the governing equations for structural mechanics, maybe for heat transfer, maybe for fluid mechanics. And then it takes those differential equations, it works through, the weak form. We do the integration, we bring in, little brother weighting function, right? And so it goes through that whole process in order to derive a matrix, that describes the physics of that problem. And so that was kind of the whole point of that entire section. Right? And then the last kind of big area for this class, which is going to be our focus for the rest of the class, is the application for this in ANSYS. Okay? And so ANSYS, of course, that's our commercial software of choice, and so that's what we're using to do the whole thing. And ANSYS kind of does the whole package for you. Okay. And so my approach with kind of the ANSYS, and with all the activities that we're doing this semester is really just to kind of show you guys all the different features that are within ANSYS, because ANSYS is a huge software. And so, we're going to be doing 6 activities in this class, but even then, there's still a bunch of stuff in ANSYS that, we just don't really have time to cover. And so my goal with all the ANSYS activities is to kind of give you just an introduction to all the features that are out there and give you a chance to apply it to a problem of your choosing, so that you can kind of take that kind of basic instruction and kind of, take it to the workplace, if you are going to be using finite elements in the next stage of your life, and kind of as a starting point to learn more about the software. And of course, to learn more about finite element software, you have to have a good grasp of finite element theory, which, you're going to get from kind of these two sections here combined. Okay. And of course, one thing that, ANSYS does that, even in the strong form, weak form section that we didn't really do is meshing the geometry, right? And so that's kind of been a big focus of our ANSYS activity so far. So how do we mesh the geometry? What size of the elements do we use? And we're going to be talking a lot more about meshes going forward as well. Okay. All right. And so this diagram ended up being a little bit more messy than I thought, but hopefully this kind of helps kind of pull things together about kind of everything that we've done in this class so far, and kind of give you kind of a look on kind of where we're going and how it all kind of pieces together. Right? Because in reality, finite elements is a difficult topic, and honestly, like you guys are doing something that I didn't do, which is take finite elements at this level, and so I didn't actually learn finite elements until I was in graduate school, and for a lot of engineering programs, kind of around the nation, finite elements is really just kind of a graduate thing, and so you guys are learning very complex ideas, very sophisticated theory, especially at your level, and so. It's difficult, I know, and it's a lot of steps, a lot of math, it's a lot of computations, but what I'm hoping for is that from this class you get kind of a good big picture idea of what the finite element method, what's involved in that, and how to actually use the software that's available to do some practical problems. Okay, so any questions on this? Okay. And so, we'll be, just like I mentioned, for the rest of the class, for the next 6 weeks, we're going to be putting a big focus on ANSYS and kind of, moving forward with that, especially with the meshing. So, we're going to be spending a lot of time talking about different element types. We're going to be talking about mesh convergence testing. We're talking about, verification, validation, because that's kind of a big kind of sticking point for a lot of people doing finite elements. All right. And so with that, let's go ahead and continue where we left off before spring break, talking about 2D element types. Okay. And so this is kind of the precursor to 3D element types. And so we've done one 2D analysis in this class. That was our first ANSYS activity. But as you all know, we live in a 3D world. We don't live in 2D space. But before we learn 3D stuff, we have to learn 2D first. It's like learning how to walk before you can run, right? And so what we covered kind of before the spring break was that we had two main shapes for elements. Okay? We had a square and a triangle. Okay? And the square, the name that we call it is a quadrilateral. And the triangle is just a triangle. You can just call it like that, okay? And the way that I'm going to present these elements is I'm going to present what their shape functions look like. Okay. And then also talk about some of their general properties. And both element types here, both the quadrilateral and the triangle, they're going to have both a linear version and a quadratic version, right? And so that's kind of one thing that we talked about before the spring break, is that when you're doing finite elements, you can either use linear shape functions, for your element, or you can use quadratic ones. Okay. And then I believe kind of where we left off was kind of with the quadrilateral. And so let me kind of work on that first, okay? And so let's do the linear quadrilateral. Okay. And so the linear quadrilateral, it looks like just kind of the shape that I drew up there. Okay. And the thing with linear elements that, and this is a property that's shared with all linear elements, the nodes or the vertices, basically where I drew the dots, we only have those at the corners of the element. Okay. And so let me go ahead and label these nodes. We'll call this node I. I'll call this node J. Or let me see, is that the, yeah. We'll call this node M, and we'll call this node N, okay? And then let's also define this in terms of the isoparametric coordinates. And so these are the Gauss coordinates that go between -1 and 1, right? And so the x-axis, we call that epsilon or tornado. And then for the y-axis, we call that eta or fancy n, right? And so let's define the shape functions. Okay. So first we have SI, and so this is the shape function that's associated with node I. Okay. And so SI is going to be 1/4 1 minus tornado times 1 minus eta. Okay. SJ looks very similar, and so we have 1/4 1/4 times 1 plus tornado times 1 minus eta. Okay. Then we have SM, or the shape function associated with node M. We have 1/4 times 1 plus tornado, 1 plus eta. Okay. And SN, this is going to be 1/4 times 1 minus tornado, 1 plus eta. Okay. And so we have 4 shape functions here for the 4 nodes. And if you perform the multiplication for these, for these shape functions, you'll see that there are linear functions with one cross term, right? So we have one term that's eta times tornado, and so that's, even though that's technically a quadratic term, it's both eta and tornado are linear, and so there we say it's basically quasi-linear. Okay. Okay. So any questions on this so far? Okay. Right, so that's the linear quadrilateral. And then one thing I want you to remember, as we go forward, that this guy has 4 nodes per element. Okay. And then we're going to contrast that with the quadratic quadrilateral. Okay. All right, so the quadratic quadrilateral looks like the following. And so we're going to have nodes at all the corners of the quadratic one. Okay, but in order to actually form our quadratic functions, we need additional mid-nodes, right? And so that's a property of all quadratic elements, that you need additional nodes at the middle of all the edges. Okay, and so let's go ahead and label all these nodes so we can write their shape functions. Since we have IJ, M, and N, and so those are the corner nodes. And then the mid nodes have the following labels. And so we have node O, we have node L, we have node K, and node P. Okay. And we have the same coordinate system here, where the origin is at the center of the element, and then we have the x-axis and the y-axis. Okay. All right. And so, since this is a quadratic, element, our shape functions are also going to be quadratic. Okay. So let me go ahead and write down. I'll write down some of these shape functions, but it's kind of a lot. And so, if you want to see all of them, you can look at them. You can look at them in the notes. Okay. All right, so let me write out a couple of the corner shape functions. I'm not going to write down all of them because, these are things that would be kind of embedded into the code within ANSYS. And, I'm not going to expect you to do any calculations for them, but I want you guys to at least see them just to see, just see what they look like and to see that they're quadratic functions. Okay. All right, and so let's do SI. All right, so this is the shape function associated with node I, and so this is going to be -1/4 times 1 minus tornado, 1 minus eta, and then 1 plus tornado plus eta. Okay. And then let's do the shape function for node M as well. Okay. And so for node M, we have 1/4 times 1 plus tornado, 1 plus eta, minus 1 plus tornado plus eta. Okay. And of course, we can have shape functions for nodes J and N as well, and they look similar, but the signs are a little bit different. Okay. But you can see, if you actually FOIL out these expressions here, you're going to get a quadratic function in both tornado and eta. Okay. All right. So now let's talk about the mid node shape functions. Okay. And so I'm just going to do 2 of them. And so let's do one for node K. And so SK is going to be 1/2 times 1 minus eta times 1 minus epsilon squared. Okay. And then we have, let's do SO. Okay. It's going to be 1/2 1 plus eta times 1 minus epsilon squared. Okay. And of course we'll have 2 more shape functions for let's see, nodes L and nodes P as well. Okay. All right, but the actual actual expressions for the shape functions, at least for this class, we're not actually going to be using it for anything, but I just want you to see that these are quadratic functions. Okay. And so what we'll talk about next is some of the benefits and drawbacks of either choosing linear or quadratic shapes. Okay. Before we do that, are there any questions on this? Okay. All right, and so let's talk about some properties or some considerations that you can make between linear and quadratic elements. Okay, and so the first thing, that you should notice is that per node, linear elements have less nodes per element. Okay. Okay. And so if we just look at the quadrilaterals that we just looked at, right? The linear version of the quadrilateral had 4 nodes, okay? And the quadratic one had 8. And so that's a 2x increase, okay? And so, if you're going to go to quadratic, it's not exactly 2x because, the nodes will share, the elements will share nodes next to each other. And so it's not quite a 2x increase in the cost, but it's, it's significant. And so it's something to really, something to think about, okay? But that cost doesn't go to nothing, right? And so you're not just paying for nothing, because when you use quadratic elements, you can generally expect that you get more accurate results. And so you pay a little bit more with quadratic, and it takes a little bit more memory, a little bit more time, but it really pays off. Okay. And in particular, where quadratic elements really shine are in kind of two situations that actually happen quite a bit. Right. Right. So quadratic elements really shine in cases when you're interested in derived quantities. Okay. Okay. And by derived quantities, I mean, solutions that you don't directly solve for from the finite element expression. Okay. And some examples of this could be things like stress, right? So that's one thing that we've seen quite a lot. Right, so things like equivalent stress, maximum principal stress, normal stresses. These are things that aren't directly solved for from the finite element solution. And so if you kind of think back to our finite element forms, or even our trusses and our beams too, right? So when we perform the solution in MATLAB, we did A\B, we weren't solving for the stresses. What we solved for instead was the displacements. And then from those displacements, we were able to compute things like stresses from that. Okay. And so, this is, even though, it might seem like we're just doing two calculations here, it's pretty significant because, we're kind of performing two levels of calculations. Where on the first level, the first level calculations, when you do your A/B, and this is after we do we form the element stiffness matrices, we do the assembly and the boundary conditions. I consider this to be kind of the primary finite element solution. Okay. Okay. And so these are things that are directly solved for from the finite element problem. So things like displacement, things like temperatures, right? And so these are kind of primary solution variables. And so, whether you choose linear or quadratic ones, they both do pretty well in solving for the primary ones. But oftentimes, when you're going through the trouble of performing a finite element, you're interested in things other than just the primary solutions, right? And so, if you think of all of our ANSYS activities so far, we've looked at the deformation, and the deformation is fine, and it's good to look at. But we've also looked at things like stresses, because that's where finite elements really comes into play. And so the way that ANSYS compute these things is that it takes your primary solution, and then it performs additional calculations on that. And the way that ANSYS does this is that it actually uses the shape functions again for this. Okay. And so the quality of your shape functions really affects the quality of how you compute the stresses. And so if you're really interested in the stresses or some kind of derived quantity from your FEA, quadratic elements really shine because they're going to end up with a much more of an accurate solution, much more of a reliable solution than if you use linear finite elements. And so that's one situation where going quadratic makes a lot of sense, and that's kind of generally why when we do structural finite elements, we generally use quadratic elements, 95% of the time, because most of the time, we're interested in those stresses because that's going to tell us if our material is going to break or if it's going to bend, right? And that's really important to know if you're designing a structure, right? Okay, and so the other place where quadratic finite elements really shines and gives you much more accurate solutions is if you have large solution gradients in your solution. Okay. And what I mean by that is, when you say that your solution has a high gradient or a strong gradient, what we mean is that the solution is changing rapidly over a small amount of space. Okay. And so think back to ANSYS activity 3, right? So when we were designing the signpost, right? And so if you remember from the signpost, right at the kind of the edge, and pretty much everyone got this from the activity, you had a very high amount of stress, right, where it's rooted, and then the stress kind of fell off really quickly from there, because that only just that part where it's fixed, that's handling most of the stress, right? And so what you can say there is that you have a very high amount of gradients where you go from extremely high stress to really, really low stress. And that happens over the course of, a very small amount of space, right? So over the course of, inches, centimeters, whatever, right? And so in cases where you have these high gradients or you have this rapid change, I would feel a lot better if, as an engineer, as an analyst, I'd feel a lot better if quadratic elements were used rather than linear elements, because linear elements kind of tend to it kind of tends to not capture these rapid gradients as well. Okay, so any questions on this so far? Okay. Right, so quadratic elements, more expensive, but generally the cost is worth it. Okay. All right. Let's see. But the thing that you have to be careful for with quadratic elements is that as you increase your dimension, right? So as we go from 1D to 2D to 3D, the cost of going quadratic increases. Okay. And so it kind of becomes a much more important decision, as you go up in dimension. Right? And so just to kind of illustrate this, let's consider our 1D case, right? And so when we were considering our 1D elements, a linear 1D element only had 2 nodes, right? So let me make this the linear column. I'll make this quadratic. And so when we went to quadratic for 1D elements, we ended up with 3 nodes. All right, question. So the cost is worth because it converges faster. Is that always true? It's tough to say whether something's always true, just because whenever you say something is always, everyone's like, well, actually, someone will come up with a counterpoint. But I would say generally 99% of the time, going quadratic, it helps you converge faster. Yeah. So what Ronald's talking about with convergence means is that as you refine the mesh, and so as you go from a fairly coarse mesh to a finer mesh, with quadratic elements, you approach a very accurate solution much more quickly than you do with linear fine elements. And so I can't think of a case off the top of my head where that wouldn't be the case, but there might be something out there. So I will say with strong confidence that 99 and I'll say 99.5% of the time, quadratic elements will give you faster convergence than linear. Yeah. The difficulty with using quadratics is actually more in the programming. And so actually, I've actually never worked with quadratic finite elements until I started using ANSYS when I started working here, because in my past, I've worked on kind of implementing and developing my own finite element codes for research, and usually quadratic elements was just too much of a pain in the ass to really kind of deal with when you're implementing it in code. And so, that's kind of the main difficulty with quadratic elements. But if you're using a software like ANSYS, where some engineer that works for ANSYS has done it for you, quadratic elements is usually the way to go. All right, and so let's look at our 2D case. And so for our linear 2D finite element, we had 4 nodes. And then when we went quadratic, we went up to 8 nodes, right? And so if we just kind of quantify the amount of cost increase here, okay? And so for the 1D case, we have 50% more nodes for our quadratic element. And then for the 2D case, we have 100% more nodes, right? And so that's twice as much. And I know we haven't seen it yet, but I'll give you kind of a sneak preview of 3D. Okay. And so for the 3D linear hexahedron, which is our brick element, we're going to have 20 nodes or eight nodes for the linear one. And then for the quadratic one, we're going to end up with 20 nodes per element. And so it's quite a sight to behold, actually. Okay. And so and this is going to be an increase in 125%. Okay. And so, as you go up in dimension, the cost of going quadratic is increasing. And so that's kind of one thing to keep in mind. But the nice thing about quadratic elements is that usually you don't have to have as many elements in order to get an accurate solution too. Okay. And we'll talk about this more later too. Is that we're talking about accuracy in terms of linear versus quadratic, but it's not that you can't get an accurate solution with linear, because if you're kind of constrained with linear elements, either because you're writing your own finite element software or for something else. The way that you get an accurate solution with linear finite elements is just to refine your mesh. So just kind of throw just a bunch of more elements in there, and most of the time that works. And so that's at least for everything that I've personally done, being stuck with linear finite elements, I was able to get good accuracy just by using linear finite elements and just refining the mesh like crazy. Okay, so that's definitely an option out there. And so the idea with quadratics is that you can achieve the same accuracy with less amount of elements. And so, there's kind of, more than one way to skin a cat. And so, ultimately the goal for any kind of finite elements is to get an accurate solution, and there's kind of multiple routes in order to get there, right? And so you can either use linear finite elements and just have a really refined mesh, or you can upgrade to quadratic and maybe you don't need as fine of a mesh. And so both of them kind of achieve the same thing with some nuances in between there that, we'll talk about a bit later. But for most cases, you kind of go both approaches. Okay. All right, and so the last difference that I want to talk about between linear versus quadratic is in terms of representing the geometry. Right? And actually, some of you have kind of already experienced this a little bit. Right? And so quadratic elements. Quadratic elements, since they're a quadratic function, they can have some curves to it, right? I've always wondered why someone wanted. That's a good question too. Too philosophical for me to answer. I just use the phrase just because it's common. Yeah. All right. So quadratic elements, because we have that quadratic term, a quadratic function can actually have some curves to it, right? And so it's not just a straight line. And so that actually helps us out when our geometry itself has some curved edges. Okay. And so, the reason for this is, because isoparametric elements are used, we use the shape functions to actually represent the geometry as well. Okay. So let me give you kind of a relatively simple example here. And so let's say that we have, a geometry that looks like this. Okay. Right, so this is probably maybe something that you produce in CAD, so in SolidWorks or something. Okay. And we want to perform this, or if we want to perform finite element analysis on this geometry. Okay. If you use linear finite elements, it might look something like this. So and whenever I do this in person, I always kind of screw up this drawing. But here I can make it nice. And so with linear finite elements, where the sides of our structure here are kind of limited to be straight lines, we might get something like this. Okay. But quadratic elements, because we have more nodes per element and because we can have some curves, it's going to do a little bit of a better job representing this geometry. Okay. Right, and so we might get something that looks like this. Okay. This is where I usually mess up. Okay. And so we do a little bit of a better job of doing of representing that geometry just like that. Okay. A little bit. And so it's not perfect. And some of you experienced this in ANSYS activity 2, where even with quadratic hexes, it was still struggling to mesh. But it can help a little bit. It can help a little bit to get around some curves in your model. Yeah. And so that's kind of another good reason to go quadratic, where if you have some curves in your geometry that you want to make sure you do accurately, quadratic elements they do a little bit better than linear ones. Although if you have a lot of curves in your geometry, the better thing would probably be just to switch to triangles, because triangles just kind of naturally do that a bit better. Okay, so any questions on this before we start talking about triangles? Okay. All right, so let's start talking about triangular elements now. All right. And so kind of the big motivation for triangular elements is that, if you're using quadrilaterals, those really struggle to get around curved boundaries. Even quadratic quadrilaterals, those kind of really struggle. Okay? And so going quadratic with your quadrilaterals can help a little bit, but sometimes it's not enough, especially if you have some like really crazy geometry, which I have no doubt that a lot of you are going to do for your final projects. And so if you have a geometry that's really crazy, quadrilaterals or hexahedrons might not be able to mesh it. So you might get some meshing errors with ANSYS. Okay?
What do you consider crazy? Just
anything that has a lot of fine features, I would say. And so usually, if you have something that, so like a very gentle geometry might be something like this, right? It might just be like a step. But if you add a lot of fine features to this, where you have, maybe a little bit of bumps like here, maybe like a nice little thing right here, and it goes a little bit crazy like that, right? Now I'm just scribbling. Whenever you have, a complex geometry where, it's, it kind of does a lot of twists and turns. That's something that, you'd probably want to use a triangle for. Yeah. Okay. And so the triangle, is much better suited for this. And what we'll see later is that tetrahedrons share kind of a lot of the same properties as triangles as well. And the reason triangles are so good at this is because the triangle itself is kind of a lopsided shape, just kind of natural, right? And so if you draw your triangle like this, right, you have kind of, if we kind of look at this from left to right, we can have two ends here, right? And so on the left end, we have kind of a thin, kind of slender end. And on the right hand, on the right side, we have kind of a thicker end, because that's where kind of the other ones are, right? And so because the triangles are kind of, these kind of naturally kind of lopsided structures, they can kind of fill any space that you need to, okay? And that property where, you can use a triangle to fill any 2D space, that's called the simplex property. Okay. And the simplex property, again, is the ability to fill any arbitrary 2D space with triangles. Okay. And that's really handy because, a lot of times when you're doing finite elements, you're not doing it on just kind of like a brick or easy geometries. You're doing things like really complicated stuff, like on houses, or things like, like things on a car, right? Basically every structure that's on an engine, I would consider that to be a complex structure, right? And so, being able to take any geometry and to fill it, with triangles is a huge advantage. So that's kind of the really nice thing about triangles. Okay. Simplex is equal to simple plus complex. I'm actually not sure where the name comes from. I think simplex is another name for just kind of any kind of arbitrary shape. Yeah. And so I think that's kind of where it came from. I don't think it's an amalgamation of simple and complex. Yeah. Okay. And so let's go ahead and label these nodes, and let's list out the shape functions. Okay, so we'll call this node I, call this node J, and call this node K. Okay. And for a linear triangle, these are the only nodes that we need. So remember, we only have nodes on the corners for our linear finite elements. Okay? And so let's go ahead and write out the shape functions. And so the shape functions, thankfully, are pretty simple. Okay? And so SI is going to be epsilon. Sj is going to be eta, and Sk is going to be 1 minus epsilon minus eta. Okay. Okay. So very simple. So very simple shape functions here, and you can see that they're all clearly linear. Okay. And actually, this figure of the triangle here is not. It's not in the natural coordinates, so it's not in the Gauss coordinates. And so let me go ahead and draw that for you guys on the next page, that you can kind of see, why these shape functions are the way they are. But this is the really nice thing about triangles. And so, I'll tell you just from a developer's point of view that having such simple shape functions is a godsend. And so it really makes implementing the code a lot easier. And I won't say that I know how ANSYS was developed, but I would hazard a guess that when ANSYS was first being developed, they started with linear triangles, just because shape functions are just the simplest as you can be. All right, any questions on this so far? Okay. All right, and so kind of the natural coordinates, or the Gauss coordinates for a triangle, or the natural, I would say, configuration for the triangle looks like the following. Right? And so we have our two axes here. Okay. And so we have epsilon and eta. Okay. And the triangle looks like the following. Okay. And so we have node I over here. This one's node J, and this is node K here at the origin. Okay. And so the coordinates for this is going to be 1, 0. This is 0, 1. And of course, K is 0, 0. Okay. And so with these coordinates, you can kind of see how we got the shape functions on the previous page, because then that's if you evaluate the shape functions at each of the different nodes, you should either get 1 or 0 depending on if the node matches with the with the shape function. Okay. All right, so now let's go over the quadratic triangle. Okay. And so the quadratic triangle, we know, at this point, that we're going to take this our linear triangle and then put an extra node or an extra mid node between on each of the edges. And so here's our triangle, and then here's all of our mid nodes, okay? And so we have nodes I, J, K, and then let's see, we have node M, and then node N, and then L. Okay. Right. And so following kind of the same trend for our quadrilateral, we have twice as many nodes here for the 2D case. Okay. And let me write out just a few of these shape functions for you, just so you kind of see. Okay. Right. And so we have SI. Right. So SI is going to be tornado, and then 2 tornado minus 1. Okay. Let's do SK. Okay. SK is going to be 1 minus 3 tornado plus eta plus 2 tornado plus eta squared. Okay. And let's do one of the mid nodes. So let's do L. SL is going to be 4 tornado eta. Okay. And then of course, there's 3 more shape functions for the other 3 nodes. But I just wanted to show you guys that these are all quadratic functions here. All right. Any questions on this? Okay. And so we've kind of already talked a lot about the kind of the decision making process that you would go under if you're going to choose either linear or quadratic. And so I'm not going to reiterate that because a lot of that is the same here for linear and quadratic triangles. But now let's talk about kind of the benefits and drawbacks of choosing either quadrilaterals or triangles. Okay. And so we've already mentioned one before, is that if you have a relatively complex geometry, sometimes quadrilaterals won't work for that. And so you'll try to mesh it in ANSYS, and ANSYS will give you an error, and it'll give you some unhelpful error message like meshing failed or something like that. But most likely it wasn't able to find some configuration of quadrilaterals to fit within the geometry. Right, so that's a big plus for triangles, and so no matter what geometry you throw at it, the triangle will prevail. Okay, the downside of using triangles is that if you have kind of the same space, it's going to take you more triangles to fully mesh that space than quadrilaterals. Okay. And so you have kind of a fixed amount of space. And so let's say that we have kind of a space that looks like this, right? And if we try to mesh one with quadrilaterals, and then we mesh the other one with triangles. Okay. The quadrilateral one is pretty straightforward here. So we can just draw kind of a waffle pattern on this guy. Right? So that's fine. But for the triangles, the triangle, you can almost think of it as kind of having approximately half the amount of area as a quadrilateral, right? And so in order to mesh this, we kind of have to mesh it kind of like this. And so, I kind of butchered this drawing quite a bit, but you can kind of imagine that each of the squares that were originally there, we have to kind of split it in half because a triangle is just kind of naturally a smaller shape than a quadrilateral, okay? And so this requires more elements. Okay. And if you require more elements, that means that the cost is going to increase. All right, question. So on ANSYS, can you do a linear quadrilateral mesh for the whole body, then refine the mesh with triangles? Yeah, absolutely. And so the thing with meshing is that it's not an all or nothing thing. And so you can provide different meshes for different areas of the model, right? So we saw a little bit of that in the last activity too, right? So for the signpost. And so, the reason I had you guys do kind of separate meshing settings for the sign and for the post was so that you can apply different shapes or different orders or different sizes for the different parts of the mesh. And for most kind of practical finite elements where you're doing finite elements on a complex assembly, more often than not, you're going to be refining your mesh or providing different element types for a certain area, and then doing kind of a coarser mesh or other things for other parts as well. Yeah, so that's definitely it's definitely something that's almost required for a lot of complex problems to get your costs down to kind of a reasonable amount. And we'll see that a little bit too in ANSYS activity 4, because there's one part of our activity 4, which is basically just the concrete wall, which we don't really care about. We don't really need to measure stresses in the concrete wall. We're just running a car into it, and so the concrete wall just needs to be there. It needs to be able to hit the car, but we can have a very coarse mesh there, and we can use kind of linear quadrilaterals there, just because we don't really care what's happening there. It just has to interact with other parts of our model. Yeah. And so it's definitely something that's good to do, and definitely something to think about as you're doing your project as well. Okay. All right. And so, the primary thing that the primary driver for your decision on whether to use quadrilaterals or triangles, and same thing for hexahedrons or tets, is going to be the geometry. Whether you can mesh it with quadrilaterals and hexes, and if not, you're going to have to go to triangles and tets. Just keeping in mind that it's going to take more triangles and more tets to mesh that same space. All right. Any questions on this? Okay. All right. And so before we have 10 more minutes. And so before we go, I do want to talk about one kind of special case where in structural finite elements where quadratic elements are kind of almost needed to get around. And that's this phenomenon of shear locking. And so shear locking is something that I think has come up in conversation quite a bit throughout the semester. But now we're going to talk about what it actually it is. Okay. And so this is kind of a special situation that occurs in structural finite elements. Okay. And so you don't really see shear locking happen in like heat transfer or fluid mechanics just because the nature of the problem is different. All right, and so kind of just as a context, if you recall for structural simulations, our primary solution variable is the displacement. Okay, and so that's basically the first thing that ANSYS solves for, or any kind of finite elements for structures, is to find the displacement. Okay, and kind of like what we talked about earlier about derived quantities, is that after you solve for these displacements, then these displacements are used to compute the strains and, more importantly, the stresses. Okay. And so, the thing about, the thing about structural finite elements is that, if we kind of look at their governing equations are essentially a relationship between stresses and strains. Right? And this is significant because, when you're using linear finite elements, remember, a linear finite element basically means that the displacement is going to vary linearly across the element, right? Okay. And if the displacements vary linearly, what this means is that the stress and the strain are going to be constant across the element. Okay? Right? This is just for linear finite elements. Okay. And the thing is, if you have stress and strain that's constant over an entire element, this is something that that doesn't usually happen in real life. Because in real life, you usually have a gradient or a constant change in stress and strain as you move in space, right? And so what tends to happen with linear finite elements, that you have this, maybe say you have kind of a stack of elements like this, right? And so, what you're going to have is you're going to have stress that kind of changes from one constant value to another one, to another one, to another one, right? And then, kind of the net result for this is that because you have these constant stresses and strains within the element, and because your governing equation relies on these stresses and strains, then what can happen is that your displacements become underestimated. Okay. And so what visually, what it kind of looks like is happening is that if you have shear locking that's happening in your simulation, and you have linear finite elements, it kind of almost looks like the structure itself is kind of locked in place, right? And so you could be applying, a huge amount of load to something, maybe like a cantilever beam, and you're applying a huge load, and you would expect that cantilever beam to kind of deflect a lot. But if you have shear locking, it almost looks like that beam is kind of fixed in place. It can't really move, right? And so that's the problem with shear locking, is that the structure literally becomes locked up because it can't compute the shear and the stresses accurately. Okay, and so that's a problem. And so that's usually you don't want this to happen, because when you perform a finite element analysis, you want to get the deformations correct. And so using linear finite elements with structures, there's a lot of ways to make it work. But for a lot of cases, it's usually safer just to go with quadratic elements. Okay. Okay. So any questions so far on shear locking? I'm going to draw some images on the next slide just to kind of show you kind of what can happen. Okay. All right, so to give you kind of just before I draw the images, the reason, another reason why shear locking occurs is that basically what's happening is that you're having an incorrect computation of strain. Okay? Okay. And this incorrect computation of strain will lead to an incorrect estimation of the strain energy phenomenon. And when the strain energy, concept is messed up within a structure, this leads to kind of a much larger amount of stiffness than you anticipate. And so here's kind of an image of what can kind of happen. So this is kind of the worst case, that you have kind of a bending stress, right? And so normally, if you have kind of a square block like this, like a square element, and let's say that we apply some kind of bending moments to this, okay? And so we'll call that M1 on one side, M2 on the other side. Okay, what you kind of expect is that the element is going to kind of deform like this, right? Okay. And so this is kind of what's expected and what's wanted. Okay. But when you have shear locking that occurs, and you have only linear finite elements, you can't get this kind of curvature in this, in this image here, right? And so what you end up with is something that kind of just looks like a trapezoid. Okay. And so it looks like the structure is kind of locked in place here. Okay. And so this is bad, right? And so situations where shear locking is kind of in most in danger of happening is cases like this where you have bending loads, and it happens a lot for thin structures as well. And so if you have a structure that's pretty thin, and you can only get kind of one element across the thickness, then that's when shear locking can occur. And the ways that you can fix shear locking is you can either use quadratic elements. That's kind of the simplest fix that you can do. Or you can just refine your mesh a lot, right? And so one way that you can fix this is like, instead of having one big element like this, if you split it up into kind of lots of elements like this, in other words, you refine your mesh, that can help you get around shear locking as well. All right, so any final questions on this before we sign off for today?
Yeah, I have a question, Professor.
Sure. What's up?
So this happens only with linear elements, you said?
Yeah. So in particular, it's linear elements and a coarse and a fairly coarse image. Yeah.
Okay. All right. Thank you.
Yeah. You don't see it too much nowadays because a lot of people just use quadratic elements for these things, and if not, you refine the mesh. But it's something to keep in mind. And I think the case where this kind of ends up happening the most is that say you're performing a finite element analysis in practice, and you need to shave some cost off your simulation, right? And so you're looking for places to kind of coarsen up your mesh, and you identify this region of your mesh. Say I'm going to turn this into linear finite elements, and I'm going to coarsen this up, without really thinking about shear locking here. And so this really comes into effect, when you're trying to kind of shave some cost away from your simulation. All right, and so that's all we got time for today. So thank you guys for tuning in. And so remember, the project proposal is due Friday, and so definitely submit those if you know what you're doing. But if you're still having trouble coming up with the project, definitely come talk to me. I'd be happy to kind of help you think of a good project. Okay. All right. So thank you guys for tuning in. Have a good rest of your evening, and I'll see you guys on Thursday.
Professor?
Yeah.
Can I real quick see page 6?
Yeah. Mm-hmm.
Perfect. One sec. Thank you.
Okay, so I'd like to just ask something real quick. So I was looking for free CAD models to use for my project, and I came up with this one, and I want to know if this is like a reputable site before I start downloading stuff from this.
Let's see. I personally have not used this site before. I mean, it looks good to me. I mean, it's a beautiful CAD model of these things. So yeah, I mean, definitely, run your virus checks and everything just to make sure that it's your computer doesn't get canceled from this. But it looks good to me visually.
Okay.
Thanks, guys. Jensen, did you have any other questions? Because I do have another lecture after this, but I can stick around for 5 more minutes if you have any more questions.
Oh, I was hoping to ask about this, so I over the break I checked on the midterm because I was graded, and I wanted to say that I didn't quite agree with